Welcome to the slope-intercept form and derivative introduction. All right, so suppose we have a formula, a function, y equals 3x plus 4. So you may be able to identify from earlier math classes that this appears to be in the slope-intercept form. And we're going to break that down and look at every piece of that slope-intercept form where y is equal to mx plus b. Generally, once we're in the y-intercept form, we're looking to start graphing the line. And the first thing we want to do is find the x and y-intercept. And to find the x-intercept, we're going to set y equal to 0 and then just do the algebra to solve for the x-intercept. This slide shows the math to solve for the y-intercept, where we're setting x equal to 0 and solving for the y-intercept. So here graphically we're using Desmos to show the graph of the function y equals 3x plus 4, and I've also plotted the x-intercept and the y-intercept. So now looking back at our original formula, we've got the y equals 3x plus 4 and the y equals mx plus b is the y-intercept format. We can see that mathematically b is always going to be equal to the y-intercept. If x is set to 0, the mx part of the equation goes away and y is always equal to b. So b represents the y-intercept. Okay, so we can see that x and y in the y-intercept formula represent an x and y on the graph, and that b represents the y-intercept. So what about the m? The m is the change in y versus the change in x. Could also be designated as y1 minus y2 divided by x1 minus 2, or delta y over delta x, the change of y over the change of x. And in our formula, we can see y equals 3x plus 4. We can see that the m, in the m position, we have the number 3. So the slope is equal to 3 per the y-intercept formula. So here you can see where we want to basically measure or derive the slope from the graph. And I've changed the x-axis and the y-axis to be a 1-to-1 ratio. I picked a point that was easy to see, that was basically a whole number point. And you can see that at minus 1, 1, that point crosses the function. And if we take that, and we're moving from left to right. So if we take that and count the minor divisions, we can see that we've got 1, 2, 3, 4 from the x. So we've got a positive x of 4 moving from left to right. And from that point up, we're moving from 1 all the way to 4, and we count those individual minors, and we see that we get 12 minors. So if m is equal to the change of y over the change of x, and we can calculate the slope there as 12 divided by 4 equaling 3, which is exactly what our formula said the slope should be. Or we could even use exclusively our intercept points, and we see moving from left to right that we get an x of 4 divided by 3 and a y of 4 if we wanted to use the major divisions. And that also mathematically equals 3. And we know that the slope for a straight line should always be the same no matter what points. We can always take any x or any delta y over any delta x, and it should always, for this line, should always end up being 3. So here's probably the question that you have. What does this have to do with calculus? What is all this analytical geometry have to do with calculus? And so we've been looking at y equals mx plus b. We've got our example, y equals 3x plus 4. We've looked at it in depth graphically, And in calculus, there's what's called the derivative. And if we take the derivative of a function, we get the instantaneous slope, or at that specific point, we get a change in y over change in x. And in calculus, or specifically in derivatives, this is known as dy dx. So when you take the derivative of a function, your dy dx represents that derivative. The difference is in calculus compared to analytical geometry. Calculus is the slope is always changing. It's moving around. We're dealing with bendy curves. And you taking the derivative of the function, we can then find the specific slope at a specific x or y graphically. All right, so here is the intro to derivatives part. And in order to take the derivative of the function, here are the steps. So if y is equal to ax n raised to the n, x raised to the n power, then dy dx, the derivative, is equal to an x raised to the n minus 1 power. And that is always a little bit confusing at first until we work through a couple of examples and you can see what's happening there. So y is y and x is x. The a is the number in front of x, so it's some number. And n is the exponent of x, so whatever x raised to whatever power. So the easiest way to kind of figure out how to do a derivative is to just do a few examples. And so if we start with our original function y equals 3x plus 4, now we can kind of rewrite that formula so that we can see the exponents. And we get y equals 3x raised to the 1 power plus 4x raised to the 0. So anything raised to the 0 power is equal to 1. So we didn't change that 4 at all. So it's basically saying 4 times 1 is still 4. But we're putting x to the 0 power there as kind of a placeholder so that we can apply the derivative format or to the equation. So now when we're ready to take the derivative, we see that we switch the y to a dy dx. And if we apply the format we're taking now, we've got 3, which was the a, times 1, which was the original exponent, times x raised to the 1 minus 1, which is the n minus 1 power, plus 4 times 0, because x was raised to the 0 power. So basically that whole chunk of the equation, the second part, the 4x to the 0, just goes away, because as soon as you have the 0 in there, 4 times 0 is 0. So the next line, so I write NA there for the n minus 1 power because it didn't matter anyways, because we're already 4 times 0 in that section. So now the next line we see that we've got 3 times 1, and we're going to do the math of the exponents. So 1 minus 1 is 0, and then plus 0 from previous, and that gives us x raised to the 0 is equivalent to 1. So 3 times 1 times 1 plus 0. So we can see that dy dx, the derivative of our original function, is equal to 3. And as we remember from earlier, in our slope-intercept form, our slope was actually 3. So now we can see the relationship between derivatives and slope using the slope-intercept form. And so now we know that m, the slope, is equal to the change in y over the change of x, or y1 minus y2 over x1 minus x2, or delta y over delta x, and now as the derivative dy dx. All those are equivalent. And this relationship is really an important concept to understand, and we'll be using this throughout calculus. We'll be applying this concept for the rest of the semester.